Hi everyone, today's lesson is on solving two-dimensional vector problems in regards to relative velocity. Now at this point you should have an understanding of how to calculate displacement vectors algebraically if they're not in the same line together, so in two dimensions. So what we're going to do is look at this idea of relative velocity today. So let's consider this first example. Consider rowing across a river that has a current that is perpendicular to your direction of motion, so it's 90 degrees to the direction of motion. You are rowing at 10 kilometers per hour east, and the river has a current moving 8 kilometers per hour north. If you row directly across the river, you will end up downstream. So it doesn't mean you're going to end up at the end of the stream. What it means is here's a river. The river we know has a current flowing north. So the current in the river is flowing this direction to the north. And so if you draw a scale vector diagram, as it says here in part A, I don't have the scale necessarily that you have on your paper, but it's going to look something like this. This is the velocity of the water relative to the shore. So that's the river moving along. And you're also going to have this velocity of the boat relative to the water. And so when you add those two velocities together, what you end up with is a velocity of the boat relative to the shore. And you'll notice there that the boat is relative to the water is relative to the shore, and so by virtue of the first and last letters on those subscripts, the boat ends up relative to the water, or the boat ends up relative to the shore, as we see there at the end. So, with this in mind, we know that the boat relative to the water is 10 kilometers per hour in the eastward direction, and we've shown that in the eastward direction. So there's the east, there's north, there's south, there's west. And then we know this is 8 kilometers per hour in the northwards direction. And so what you should end up with, and I let my scale, when I actually did this on paper, I let a scale of 1 centimeter is 2 kilometers per hour. And so I arrived at an answer of somewhere about 12.5 kilometers per hour at an angle of east 40 degrees north. That's what the scale vector diagram showed me for this answer there, for the velocity of the boat relative to the shore. And so just based on our common everyday experience, some of us have tried to swim across or even walk across a river with a fast current. We've noticed that that current pushes us downstream. And so that's what's happening to the boat as it crosses. The nice thing about this is it ends up being a 90-degree angle. So the math is relatively straightforward. However, conceptually, there are a lot of misconceptions that students make, and so I want you to bear with me here, and let's try to address some of those in this video. It says, solve the problem now using algebra. And so I'm going to keep the diagram in place here so we can see that. And the first thing we noted is this idea of the velocity of the boat relative to the shore as a vector is equal to the velocity of the boat relative to the water plus the velocity of the water relative to the shore. And so we get the first and the last, and together, that's what this is relative to. This doesn't mean you can just put them in the equation, 10 plus 8, and get an answer of 18. These are vectors, and so a vector equation is represented by the diagram, but you have to interpret it and not use that equation directly to calculate. So what we're going to do in this particular case is we are going to solve using the Pythagorean theorem. We know it's a 90-degree triangle, so we can say that the boat relative to the shore squared, just looking at the magnitude for now, is the boat relative to the water squared plus the velocity of the water relative to the shore squared. And so we know these two values. We know the boat relative to the water is 10 kilometers per hour. We know that the water relative to the shore is 8 kilometers per hour. We need to square both these values. And we need to take the square root of that to get the boat relative to the shore. Because of the Pythagorean theorem, don't forget to take the square root at the end. So what we arrive at is a value for the boat relative to the shore of the square root of 164 kilometers squared per hour squared. And if you notice, when we square all this, the square root of these units gives us kilometers per hour, and it's 12.8 kilometers per hour. That's the velocity of the boat relative to the shore. the other thing that we're noticing here is that we're not taking the positive or negative square root when we're solving for the boat relative to the shore. This has to be a positive value in terms of a length or a speed here. So we're just going to assume the positive. So the other thing we have to do here is find the angle. And if we have a right angle triangle, we use SOHCAHTOA. And if I know the adjacent and the opposite, TOA, so that's tan is the opposite over adjacent. And what we're left with is theta is tan inverse, the opposite side is 8, the adjacent side is 10. Those both are in kilometers per hour, so the units cancel out. And we're left with 38.7 degrees, which is pretty close to what I found up above, but not exactly the same. Therefore, the velocity of the boat relative to shore is, we take two significant digits, so it's 13 kilometers per hour, 2 sig digs, east, 39 degrees north. And we can see that just from the diagram, because this is the angle I took right there, the diagram above. So it's 13 kilometers per hour east, 39 degrees north. And so now we deal with some other questions and some common misconceptions. So how long in seconds will it take to cross the river if the river is 35 meters wide? So let's just draw this again, just a quick diagram to have it on this page. We know that we're trying to go across that river, and we know that as we try to go in this direction, the velocity of the boat relative to the water, that we're going to get swept downstream of the velocity of the water relative to the shore. And so if we start somewhere like here, we're actually going to end up somewhere over here. We're not going to go directly across. We're going to end up downstream from where we started. So what do we know? We know that the time is what we're trying to find. We know each of these values. We know the velocity of the boat relative to the shore is 12.8 kilometers per hour. Just taking one more sig dig that I had there. Ideally, I'd take 2, but I just had one more there for this calculation. And the velocity of the boat relative to the water, we know is 10 kilometers per hour east. All right, we have all these givens. And so we also know that the width of the river is 35 meters east. That's how far, that's not the width of the river. It's the displacement that's going to happen going across the width of the river. So you're going to go 35 meters east. You're in fact going to go further than 35 meters because you're going to go all the way along here. But your displacement in the eastward direction is going to be this. So what happens in the north and south direction doesn't affect what happens in the eastward direction. So there's one of the common misconceptions. So I'll say that again. What happens in the north and south doesn't affect what happens in the east-west and vice versa. So really this question is a matter of saying, well, what's the velocity of the boat relative to the water? Well, the velocity of the boat relative to the water is the displacement divided by the time. Rearranging that equation tells us that the time is the displacement divided by the velocity of the boat relative to the water. Well, we have to be careful here because we know the displacement is 35 meters. And so you could put, if we've said that these two directions are positive, positive, and positive, then we could go ahead and ignore the vectors and not have to write them in the equation. But if you don't, you can always write them in the equation. It's never a problem to do that. It's just a good way of checking to make sure we have everything in the right way. You'll notice though that the velocity of the boat relative to the water is not in SI units, in these units where we have meters and seconds. And so we're going to go ahead and change that velocity of the boat relative to the water. So I'm going to turn this into meters per second. And so we know that we're trying to get rid of kilometers. So I want to have that on the bottom to cancel it with that. 1 kilometer is 1,000 meters. And I also know that 1 hour, and I'm putting that on the top to cancel it with this over here, is 3,600 seconds. So in fact, we're going to take 10, multiply it by 1,000, divide it by 3,600. We're really taking 10 divided by 3.6. And what that's giving us is 2.778 meters per second in the eastward direction. All right, so we can go ahead now that we have meters per second and we can sub that in. 2.778 meters per second east. because the directions are the same, the directions cancel out, I don't need to worry about those, and we're left with a time of 12.6 seconds. And we can conclude to two significant digits, therefore it will take 12.6 seconds to cross the river. Now here's, again, the misconception. The time it will take to cross the river with no current is exactly the same amount of time it will take to cross the river with current. Because the entire time you are pointed across the river with the same speed in that direction. Let's look at the next question. How far downstream in meters will you end up? All right, well in this case we're talking downstream, so I'm going to talk about the y direction. And I could have clarified that on my diagram up above. This should be the positive x direction and the positive y direction. Again, I'm just going to include a diagram here so we can see this again. There's my velocity of the boat relative to the water, velocity of the water relative to the shore, and then the velocity of the boat relative to the shore is that. And so positive x, positive y, and we don't know how far downstream it's going to land. We do know it's taken 12.6 seconds. We do know that the velocity of the water relative to the shore, that's in the same direction as the displacement, so that's the one we're interested in, the water relative to the shore. We know that that is equal to 8 kilometers per hour. We're going to do the same unit analysis that we did before, dividing by 3.6. So there's my 1,000 meters, 1 kilometer, it's going to cancel out. There's my 1 hour and 3,600 seconds again, just to check that unit analysis. And we know this is in the northern direction. So we're going to have a velocity of the boat, water relative to the shore rather, of 2.222 meters per second north. Okay, that's all we need. Because we know that velocity in any direction, in this case in the y direction, water relative to the shore, is the change in position of y, or the displacement in the y direction, divided by the change in time. And rearranging that to solve for the displacement in the y direction gives us water relative to the shore velocity times the time. Subbing those values in, we get a value for the delta d in the y direction as 28 meters. Well, what can we conclude? And notice this is north too, right? Because we have to include that direction. We can conclude, therefore, the boat, or you, it's talking how far will you end up. So therefore you will end up 28 meters north downstream. There you go. The last question asks this, and it's purely a physics question. It's not trying to get into the math here. It's just simply asking, what could you have done to ensure that you rode directly across the river? Well, we saw, if you watched another video that I had on my playlist, there was this, we know that the angle originally was around 39 degrees. That was the angle, here's directly across the river, that you would have to be swept down the river at. And so what we're trying to do is, instead of being swept down the river and starting here and ending way over here, we're trying to start here and end here. And in order for you to do that, you're going to have to go with some angle here. But here's again a misconception. Some people think this has to be 39 degrees. But that is not the case. It actually has to be bigger than 39 degrees. We'll label this as phi, the Greek letter phi. Phi must be bigger than 39 degrees. Well, why? It's because the component that's in the x direction, so if you think about it, if you're rowing at 10 kilometers an hour in this direction, the component, the part of it that's in the x direction, here's the x direction, the part in the x direction, is it 10 kilometers per hour? No. It's less than 10 kilometers per hour. And because it's less than 10 kilometers per hour, it's not going to get across in the same amount of time, and if it takes more time, it therefore needs to be at a greater angle than 39 degrees. So we can conclude phi must be bigger than 39 degrees since the x component of this motion would be less than 10 kilometers per hour. So there you go. That's our conclusion there. You didn't ask you to calculate anything, but you just have to note that must be bigger than 39 degrees. All the best with your questions now as you work through this.